What's going on, everybody? I have a special guest today. It is Scott. He has come here with his fancy little invention, and we have been messing with this infinity some more. So what do you think?
Well, we were able to, with the help of a known good, we actually have another vehicle over there that's the same setup.
One of my dealer friends and borrowed a whole nother vehicle with the same engine, so everything mechanically is identical.
But yeah, we were able to use the ADDI and be able to visualize the high pressure common rail recharges from the high pressure pump. And we were able to clearly demonstrate that it is certainly mechanically out of time. The big question for us is we have a high pressure condition on this, and I know there's been a lot of discussion on the comments on his last video regarding this. And I have the same questions myself. But the way we've found that this thing works is when you unplug the spill solenoid, it goes to maximum pressure. When you put power and ground to the spill solenoid, it goes to minimum pressure and it won't even start. So we know that current flow is what's actually causing it to reduce the pressure. So it increases duty cycle to drop pressure. The thing for us that's really, and if anybody has any thoughts, we're going to put these scope captures up and you guys can look at the pressure and all the timing related to everything. Maybe you can we can all put our heads together and maybe see something that makes sense with this. But we were able to show, how many degrees did we figure it was out? We did
almost 90.
Yeah, it's almost 90 degrees
about
out.
85 or something like that.
Of crank rotation. So I guess we're going to go ahead and we're going to show you some of these captures that we've taken. We kind of have a money shot here, for lack of a better word.
Yeah, y'all are going to be able to see the screen captures here. I got the screen recording going. But there's one thing that we really kind of nailed between the two. On our known good, we unplugged the spill valve to break it, to make it have high pressure, because we want to see the peak pressure time in relation to, we just use number one ignition sync to have a baseline between this broke vehicle and the good vehicle. So on the capture here, we have ignition 1, our sync right here, and this is the good vehicle. Our peak pressure is coming before the ignition. Okay, here's our broke vehicle. Our peak pressure is now after the ignition. And going between the two, doing some measurements, we come up with about 85 degrees. So our peak pressure is shifted to the right, which would be later. And yeah, it's definitely 100% confirmed right there. Pump timing is out. We're still having a hard time wrapping our head around why the spill valve can't bleed the pressure off. Let me pull up that capture. I'll just show you, because it is so confusing, because we can see the spill valve flowing current. The ECM is turning it on
at the proper time.
It should be trying to bring the pressure down. Go away. So you can see right here we have our pressure coming up, but we also have the spill valve turning on right here. It should be dropping that pressure. It's just like it can't, and then all of a sudden we get drop in pressure, and then right here we kind of think it's still trying to bleed some pressure out of the rail, but it just can't for some reason. So maybe still have a bad pump. It is a new pump. New doesn't always mean good. If I don't know if I've said it on the channel or not, but new stands for never ever worked. So it's never worked when it's new. So we don't know. It could be a bad pump. But mechanically, it is also out of time. And that was the main thing we wanted to prove. We could prove timing of the pump we just actually had to get a known good to compare with, because when we were seeing this spill valve, we were like, wait, this just isn't making a whole lot of sense. So I called up the dealer and said, hey, can we borrow this? Sure. So luckily both of these trucks are theirs, so it's no big deal for them. You got anything else?
Well, I mean, the other thing with that is if you look at the service information, it says that the pressure is regulated by controlling the inlet feed. Mm-hmm. And we know that the pressure increases when there is no current flow. So we're thinking something maybe along the lines of it has to do with when that's happening. And that because the timing isn't exactly right and the piston in the pump is not where the ECM is expecting it to be, it may be affecting when it's giving it that inlet draw, and it may be affecting the pump's volume as a result. That could explain this, but there's not really any way to prove it that I'm seeing at this point.
Yeah, I spent a while this morning going through all data, trying to find all the information I could on this high pressure system, and I've got some screenshots. I will post them in here as well. Kind of shows the internals of the pump, how it works, like when it's on its suction line or its suction draw or inflow, the piston is on its way down, sucking fluid through the check valve, and then it shows it on its spill valve or its spill flow. How do they say that? Spill.
Inflow, outflow.
Yeah, inflow, outflow. Yeah. Let's see. Y'all will be able to see this. I'll post these screenshots and everything, but yeah, inflow, spill process, outflow, and this is all in relation to when the cam is rotating. So what we're having a hard time is when the valve here, the electrical part, is energized. It's really hard to figure out where this is in rotation and why it's not able to bleed the pressure off. So still a little bit of a question of why we have high pressure, why it can't bleed the pressure off. It's just one of those things that somebody smarter than us is going to have to figure this out. But we was able to prove mechanical timing is off for the pump. So I think that's about it. Anything else?
No, I just wanted to take the time to thank you for letting me come hang out with you and put our heads against the wall.
This dude's awesome. I posted the video on this thing, and it was like the next morning I got an email. Hey man, I want to fly in. I want to do some tests on this thing. I'm like, sure, come on, man. So he come here, flew in, got here this morning, and we've been messing with this. It's 7 o'clock now. He got here about 1.
About 1, yeah.
Yeah, so we've been messing with these two trucks for quite a while, and I think we've learned some stuff. It's nice having a known good.
Right.
And I'll bring up a known good, what the actual good looks like. Let's see. I think this is the correct one. It's quite shocking, the difference in the pressure. The way this ADDI works is almost like a pulse sensor, wouldn't you say?
It highlights the changes very similar to how a pulse sensor works. So if there's a large variation in the signal, it will exacerbate it to a point where it makes it stick out, and you'll see that. You'll see the difference here. But when you have an even signal that doesn't have major changes, it's a much tighter pattern.
So this is our known good here. You can see the spill valve right here, our ignition here, and injector 1. But look how nice and even that rail pressure is. That's pretty good. So quite a difference between broke and known good. So I think that's going to cover it. Like I say, I'll put some screenshots in here of all the service information I could find on how this pump works. I'll have a Google Drive with the captures that we have. It'll be down in the comments. Feel free to download them, go through them. If you've got any questions about them, you can email me, or can I put your email in?
Absolutely.
I'll put his email down there too. So you can email either one of us or both of us like, hey, what's going on here, and we will try to help you out. But like I say, we're still struggling. Maybe somebody out there watching this can tell us why this thing can't overcome the pressure when it's commanding that spool or that spill valve open. It's really a head scratcher. But thanks for watching, everybody. We'll see you guys later.
Alright guys, sorry this video has taken me so long to get out. I've actually spent the past about 2 weeks being locked out of my Apple ID account, which blocks my MacBook from seeing my iCloud or being able to get in my iCloud, because whenever I record these, they go right on my iPhone and then they get uploaded to the cloud, and when it uploads to the cloud, it deletes it off my phone to save space. And then I just download everything off the cloud on my MacBook. But there was an update that kicked me out of the login, made me re-log in, and I set that password years ago, and I could not figure it out. And it's taken me a couple weeks to finally get Apple to let me reset it. They kept putting me on a wait thing. The first time they put me on a wait thing, for some reason it got canceled, blah, blah, blah. Very frustrating. So let's get into these screenshots of the service information and some other things I've kind of been thinking about with this thing. But first I want to just give another huge thanks to Scott for coming out and spending some time with me on this thing and showing me the ADDI that he's invented. Sadly, we didn't get a whole lot of time to show some other things that it can really do, because what we were showing was just one little tiny thing that it can do, and that is taking the raw rail pressure sensor voltage. This sensor is a voltage sensor, and it basically just kind of filters it to clean it up, and then it amplifies the variations in the voltage. Pico can do it to some degree, but in some cases, the way Pico has to do it, you kind of lose some detail that you kind of need. Whereas with the ADDI, its filtering is an actual hardware filter, not software filter. So it can actually kind of clean the signal up, but not take away some important bits that might be useful. There's a whole lot of other stuff that the ADDI can do with like misfire frequency things with a crank sensor, and then the main thing that it can really do that I don't think anything else out there can do is the scent decoding. Like a lot of rail pressure sensors are now going to a scent module, which is I'm probably going to say this wrong, a single edge nibble transmitter. Is that right? Maybe. Let me know in the comments if I'm wrong. But it's basically a module. Instead of just a pressure sensor outputting a voltage, the sensor will be a module which can actually do a few different things. It can actually, some of these rail pressure sensors now actually have two sensing elements to sensor rail pressure. You'll have rail pressure 1 and 2. And then a lot of times you may even get a fuel temperature, like a rail pressure sensor with a temperature reading. So it could even have like 3 things built in there. So you could have 2 rail pressure sensors as well as a temperature sensor. And then all that gets output on one wire. So they use a scent module, which is just, all it can do is output data. It can't take data in. It only outputs data. And his ADDI, he's actually developed the code to decode the scent and separate things out to where it knows, okay, yep, this is rail pressure sensor. Let's look at this, and then it can output a voltage for the picoscope to use and then graph. So it's a really cool tool. But let's get into some of these screenshots of all the information I could find on how this pump works. And the first screenshot here is just what the ECM is using to kind of calculate when it controls that spill valve to regulate pressure. And you can see it uses crank sensor, cam sensor, the rail pressure sensor. There's a low fuel pressure sensor as well. And then engine coolant temp, throttle position, accelerator pedal, and even battery voltage apparently. It uses all of that to calculate how much rail pressure it wants to build. It's very, very complicated, like everything that kind of goes into what it's using. So here's another little thing of kind of how the fuel flows. So you've got the in-tank fuel pump, the low pressure sensor, and this is the fuel line coming out here to the high pressure pump. And of course the ECM is controlling the high pressure pump spill valve, as well as controlling the low pressure pump. This pump's probably just, it may be trying to electrically regulate fuel pressure, or it may just be relying on this fuel pressure regulator in the tank. I didn't really dig into all that too much, but high pressure pump, of course, is basically sucking in fuel and getting fuel pushed into it just a little bit, and then it's a piston that compresses it and then pushes it out to the fuel rail, and then we get the rail pressure sensor and the injectors. This is pretty common with all GDI engines, very similar operation here, nothing really unusual here. This down here is kind of like a key information section down here. The high pressure fuel pump raises the fuel pressure sent from the low pressure fuel pump actuated by the camshaft. Well, generally, yes, the high pressure pump is on the camshaft, like an intake or an exhaust camshaft in most cars. In this car, they have its own little tiny little camshaft that is driven by the chain, the timing chain by itself. I wish right here they would have put in there that it has to be timed correctly. They leave that information out right here. But actuated by the camshaft, the high pressure fuel pump activates the high, this is another little where it gets a little confusing. The high pressure fuel pump activates the high pressure fuel pump solenoid. Is this a translation thing? Because this kind of makes it seem like the high pressure fuel pump is controlling the solenoid. But then it says based on a signal received from the ECM. So I don't, when we were talking earlier in the video how we couldn't understand why the solenoid could be turned on but the pump couldn't bleed the pressure off, or the solenoid couldn't bleed the pressure off, this kind of is unusual to me, because this almost seems like the mechanical pump has some say in whether the electrical signal from the ECM can do anything. And it adjusts the amount of discharge by changing the timing of closing the inlet check valve. And we'll get into that in just a second. It's really kind of unusual how they word this thing. And right here is like the components of the fuel pump and kind of its process of how it builds pressure. And we'll have another screenshot of this zoomed in so you can see this better. But the high pressure pump is installed in front of the engine on bank 2 and activated by the camshaft. Again, right here, I wish they would have said this has to be timed. I think I don't think I've got a screenshot of the timing chain where you actually time it. I'll pull that up too and put that in here as well. But ECM controls the high pressure fuel pump controls solenoid valve built into the high pressure fuel pump and adjusts the amount of discharge by changing the suction timing of the low pressure fuel. So with this pump, we've basically got 3 stages. We've got the inflow, where it is getting fuel coming into it. The spill process, where it is adjusting the amount of fuel that is contained in the pump. So on the inflow, it is letting fuel pressure come in, the low pressure fuel getting pushed in, and then the spill is basically letting the high pressure pump push some of that fuel back out until the piston gets into the range of where the computer can say, okay, this volume should equal this pressure coming out. And then we got the outflow, where it actually pushes that off into the rail. This is kind of what we were having some struggles with. So right here, you can see the cam is rotating clockwise, right? And once we come off the height of the lobe and we get into the flat here, the piston is moving down. So once the piston is moving down, we should have low pressure fuel coming in. So this piston is also going to create some suction as it's coming down. So we got pressure pushing here, some low pressure pushing, and then we've also got the pump sucking. So that should overcome the spring pressure right here and pop open this check valve. So fuel comes into the chamber as the piston is going down. Once the piston or the cam starts to roll over where it starts going back up, you can see this is still open on the spill process because the electrical solenoid section that the ECM is controlling keeps that check valve pushed open. So it keeps it pushed open so the piston can push fluid back out of it. Okay, once this shuts, so you see it shut here, this internal spring pressure shuts it, the pressure built from the piston then opens another check valve right here that pushes all that pressure out to the rail. And the signal that we are seeing, you can only see those spikes when that valve is open. So that is when we've got pressure actually going into the rail. So we're not physically seeing where this cam lobe is. There is no way of knowing physically where that is. There is no cam sensors for it. It's on its independent little camshaft. There is no physical way of knowing the timing of that. We were judging timing based purely off of when this check valve opens and pressure hits into the rail. We see that pressure spike into the rail. So we know there's a timing issue just based off of when this check valve opens. We don't know the mechanical limitations of that check valve. Okay, like what pressure does this check valve open? Well, it's got to be less than 500 because the rail pressure on the known good at idle was 500. Generally, most GDIs idle at 400 to 500, 600 psi range. So we know it's lower than that, but we don't know 100%, when that opens or not. So we're best guessing the pump is 90 degrees off. So basically, where here it thinks it should be on an outflow, it's actually sitting on a flat, so it would actually be down. Cam wise, we would be kind of on this inflow when it physically should be on an outflow. So what what I'm thinking is, if the cam was 90 degrees off, when this starts to roll back around to control this spill process, what if the pressure is built in a way to where the solenoid, the electrical solenoid, can't physically overcome the pressure that's sitting behind it? And that's why it couldn't bleed the pressure off. And then once it's kind of rolled around some more, it was maybe able to open some. We would have thought we would have seen a large drop in pressure, but we didn't really see that. Okay, so I'm sitting here editing this, and it finally clicked on me why the pressure doesn't drop off. Okay, so think now, check valve open, pressure pushed into the rail, check valve closes. Okay, the spill valve, like I just stated here, is mechanically getting stuck to where it can't pop open and release pressure. All right, now think, once that check valve is closed on the outflow check valve, once that is closed, can the spill valve lower the pressure that is in the rail? No, it cannot. That is why we have high fuel pressure. There we go. It finally dawned on me. It finally clicked. So, like I was saying, we see rail pressure. Okay, that is outside the pump. The spill valve is only lowering the pressure based off what comes into the pump. So pressure comes into the pump. As it starts to rotate up to build pressure, that spill valve is open to bleed off pressure into the low side that the pump is creating. Once that is closed, the pump then pushes it into the rail. So in their case, the timing is off to where when the pump is actually physically pushing pressure out, the spill valve cannot regulate the pressure that is being built because it's already happened. The pressure has been built, shot into the rail, that closes, and then the spill valve can't actually regulate what is coming into the pump, or well, keep being pushed back out of the pump physically. So we got the low pressure fuel being pushed into the pump is compressing it. The spill valve can't really change what is happening on the compression stroke of that piston. So that is why we're not seeing the rail pressure drop, because the timing of the spill valve in relation of when the pump is actually compressing is not correct. Pressure is still going into the rail. We're not seeing the rail pressure lower because there is no physical way for it to bleed off rail pressure. Only adjust the volume of fuel coming into the pump. So, staying in the pump. So hopefully that makes sense. And it just clicked on me while I was editing this. So yeah, let's get back into it. And I kind of think in the waveform, you could see in the current waveform where we had the current ramp up and it was flattened off, and then there was like a little bit of a dip and then it kind of flattened back off again. I'm almost wondering if that little dip was maybe the actual pintle moving to pop open. Maybe that first section of it was actually physically held shut, and then it finally got enough to where it could pop some pressure off and open up. But I'm not real sure. Maybe this thing could never open it because it always had so much pressure that it just couldn't overcome the pressure that was already built up in the rail, just due to the timing being off. That's kind of my thought on it, is the spill valve is actually never working, like never physically opening, just because how the timing is. Now it can still draw some fuel in, because once it gets on the flat, once the cam is on this flat, you know, that piston's all the way down, and the low side fuel pressure here is going to push this check valve open to get fuel in here. And then once it starts back up, pushing back up, that gets pushed shut. And then just the electrical timing of how the ECM is trying to control this thing, the electrical timing of this thing is just off so much from what the cam is, it can't physically push that back open. That is my thought. I've had almost 2 weeks, probably over 2 weeks, to kind of think about this thing and kind of process it. And that is kind of my thought process, is there's just so much rail pressure built up that this valve can't physically open when the ECM is trying to open it. In the first video, y'all seen that the spill valve does work. I could send straight power to it all the time and get that rail pressure to drop. So we know the spill valve can move, and the reason I think that was able to happen, well, is because once this got down all the way onto the flat and we've lost this pressure in this chamber, we start having this low side come in, pushing that check valve open. Once I electrically hit it manually and pushed this valve open, that basically kept this pushing all the pressure back out. So it wasn't actually like getting in this kind of timing issue where the ECM is timing it in a way, but it's already got too much pressure built up on the inside in this little chamber and the rail that it can't move that back open. So that's my thought on that. Let me know down in the comments what you guys are thinking. Up here we've got the mark for the exhaust cam, the intake cam, and then we've got the dot on the high pressure pump. And you can see on the chain link there is a line up for that as well. So we've got chain link mark, and then one behind the cam for the high pressure pump right there. So this pump has to be in time. It's got a timing mark for a reason, and we know that this is out based off of our pressure pulses going into the high pressure fuel rail. So I wish they would put that little bit of information in the operating descriptions that I found. I didn't find a whole lot of like really good detailed descriptions about it. What I found, y'all seen. So that was everything I could find on how this high pressure pump works. As far as what information ADDI has, maybe somewhere in here there's more information about it. I just couldn't find it. So if you're Nissan tech, Infiniti tech, and you guys know some more information or where to find more information, please let me know down in the comments, because I'd actually like to read some more on this system just to know more about how it works, how it kind of does this timing thing. Because this one's really strange. This one uses two lobes to run the pump and get all the pressure into the rail. So from what I could see, the number of teeth that is on this cam is the same number of teeth that is on the crank. So for one crank rotation, this gets one full rotation. So we'll get 2 pressure pulses per cylinder or per engine rotation. That's this thing's moving pretty fast. Most of the time you'll see these on the camshaft, which run half speed of the crankshaft. So you would get, like, if it's a V6, you'll get 3 lobes. If it's a V8, you'll get 4 lobes. I've even seen a lot of the 4-cylinders will have 4 lobes. They'll give 1 lobe per cylinder. This one has 2 lobes, so V8, 2 lobes, 1 lobe has to run 2 cylinders. Let's see, 4 cylinders. So yeah, 1 lobe runs 4 cylinders, 1 lobe runs 4 cylinders. Kind of. It's how they've got this thing running so fast. I know there's a lot of you guys that have commented like this is a known issue. They wear the bucket out and stuff like that. Well, think about how fast this thing is moving. This thing is moving crankshaft speed. So yeah, that is a lot of wear on basically a flat tappet lifter is essentially what is in this thing, is a flat tappet lifter. Very, very poor design in my opinion. They should have put a roller on that. I think all the GMs have a roller lifter bucket kind of thing instead of just a flat tappet. So yeah, very, very interested to know if there is actually more information out there on this system. And I think that's about all I've got. I hope you guys enjoyed this. Thanks for watching. If you're still here, appreciate that. So thanks for watching, everybody, and we'll see you guys later.